Simulation and risk analysis. Today we will be discussing on this particular topic as to what exactly simulation is all about it and why simulation is required and how do we uh, understand the nitty-gritties of the risk thereby with the help of simulation. That would be the crux of today's videos. The agenda is simple and straight. We will go through the basics of computer simulations. For example, the simulation concept, the terminology, when is it useful, why is it useful, how to approach a simulation, and probably how to run or probably develop a simulation thereby. So yes, the simulation concept, the terminologies, when it is useful, why it is useful, how to approach a simulation, and probably how to develop and run a simulation thereby. How to interpret and analyze the result is the crux of the presentations for there. So let us understand what is simulation. Let's say banks would have said Banks is the name of a gentleman, right? Simulation is an intimation or imitations of operations of a real world process or a system over a period of time. It involves the generation of artificial history of a system and the observation of the artificial history to draw inferences. And this is what being banks been said exactly is to be defined as simulation. Whatever the real life scenarios, if we extrapolate it in a different time zone, we should be able to mimic what is going to happen, and that is what is simulation is all about it. According to Law and Kelton, in a simulation we use a computer to evaluate a model, let's say a system, perhaps numerically, and data are gathered in order to estimate the desired true characteristics of the model thereby. More specifically, and but still superficially, what I wanted to say is we develop a model for some real world system that we hope to present, and essential characteristics of that system as on when on basis does not need to represent the system, just the relevant part. Remember, we are trying to observe one particular aspect only and nothing beyond it. Why do we use such program? Probably to test or analyze a particular model, carefully choosing the input output variances thereby. We use a result for the program to make some educative guesses, deductions about the real world system thereby, and that is what simulation would be looking into it. I would request the audience of this particular video to visit wikipedia.org and probably backslash computer simulation. You will find endless amount of data and information regarding computer simulation. Very interesting info. Since I have a very small time with you people to make a video, I'm just giving you a link. Everybody must have heard about Wikipedia, everybody must have heard about computer simulation, and you should be getting into it. So why and when do we use simulation? That is fairly intuitive. Everything needs to be understood. Let's say we consider a very arbitrary large system. Let's say we name the system as an X. And now, could it be a computer system? Could it be a highway? Could it be a factory? Could it be a space probe? You name it, and we can do the system around it. So yes, we would like to evaluate X under separate conditions. Let's say we will build the system X and generate condition that examine the system per se. Why? Now, there might be reason why people might say, why are you doing it? Why not do it in the real world scenario? Probably there are plentiful of reason to simulate the situation. Why? Probably system X may be difficult to build, or system X might be very expensive to build. Either of the cases is prohibitive in nature. So we may want to build X unless it is worthwhile. And probably I don't want to waste all the dollars that I'm building upon it, right? The condition that we are testing may be difficult or expensive to generate for the real sense of the case. I'll give you an example for you to understand why simulation, why simulation, why simulation. What is the importance of simulation? Let's say a company needs to increase its production, but needs to decide whether it should build a new plant or it should try to increase production in the plant itself. How do you increase the plant within the existing capacity? Probably run it 24 hours a day. Absolutely. Instead of one shift, multiply the number of shifts from two to three or four. Probably. What options are there which makes a cost effective of the plant? Do you go for it, or should you establish a new plant altogether? Now you need to simulate the ideas to come to the result. Clearly, building a new plant would be expensive and would not be desirable. And that is the reason why you should go for a cost effective solution. Simulation provides that gateway. So Introduction to simulations, another example for you to understand. Let's say NASA wants to know the damage if a space shuttle will threaten upon its re-entry, and this is a pertinent, relevant problem the NASA faces. So if they want wait until re-entry to make a judgment, it is either too late, the astronauts are gone forever. In this case, it is not feasible to do a real world test per se, and that is what we are looking into it. Introduction to simulations, let me give you another option. Let's say model system X can simulate the condition, can use the simulation result to decide or help us to arrive into a certain solution. Continuing with the first example, model both possibilities of increasing the production and simulating them. So I can increase the number of shift in a in an existing location, or probably I can build up a new factory or new plant altogether. But when we choose that solution that is most economically viable, continuing with the space shuttle example, model damage, the stress that re-entry imparts onto the shuttle, that goes wrong. Determine via simulation if the damage will threaten the shuttle or not, the occupant of the shuttle or not. Note the importance of being correct out here. Absolutely, it is not only the lives of the people, it is not only the billions and dollars of investment, but please understand the amount of exercise, the experiments that they have carried out in the space, which might be beneficial for the mankind for years to come altogether. Clearly, this is not a trivial task of simulation. Simulations are often large, often complex, and difficult to develop. Just developing the correct system model can be a daunting task. There are many variables that must be taken into account. However, if a new plant cost hundreds and hundreds and millions or probably even billions of dollars, spending in order to have those thousand or even thousands of dollars on simulation could be a bargain. Absolutely a bargain to go for simulation. Note, even in the shuttle example, most of the work this needs to be done in advance. Don't have the time to design, don't want to implement this during the duration of a flight per se. So yes, this gives me ample amount of opportunities, and probably the audience should be impressed that simulation is a good idea. But then when is simulation not a good idea? Let us understand, and let me give you the other side of the coin also. Don't use simulation when the problem can be solved with a simpler and a more exact fashion. Some things that we think might be simulated can be solved analytically as such. Let's say, giving an example of n rolls of a fair pair of a dice. Absolutely, the dice which has a six sides, right? When we are relatively expecting the frequency of each possible, now it is a pair of dice. Remember, just two pair. So we can have what kind of result? If we can have the summation of the results of their outcomes, it would be 2, 3, 4, 12, and so on and so forth. That will come around it. Definitely yes. So we could certainly simulate this, rolling the dice n number of times and counting what happens. However, based on the probability of each possible result, we can have more exact answers analytically per se. Say, how many ways do we have to obtain each outcome? It can be 2 is to 1, 3 is to 2, 4 is to 3, whatever the outcome that each pair would be giving us. So there are n numbers of possibility. No, I'm sorry, there are only 36 possible outcomes in this case. So please understand how we go around it. For n rows, the expected frequency of value is I. Now that is what we are looking into it. The outcome yielding needs of number of i's needs to be divided by the total number of outcomes, and this will give me the probability of happening it. For example, for the 900 rows, the expected number of nines generated would be 900 times 4 divided by 36. Definitely is. That means probably if I roll 900 times, there are 100 times the summation of the both the dices would be probably only 100 times. Note, this is an expected value, and perhaps there might not be a whole number per se. Let's say for a 500 roll, the expected number of nines would be 500 to 4 divided by 36. That would be 55.55, right? 55.55 if I say so. So we need to round it off to either 55 or 56 perhaps. But again, be specific. It might be in the vicinity of 55. It might be 52. It might be 59. Might not be exactly the same, but it gives you a fair bit of an idea. You should be familiar with the general approach that comes around it. This needs to be understood as on when on basis. So, Don't use simulation if it is easier or cheaper to experiment directly on a real system, perhaps, as I've given you an example. Let's say in an example of a 24-hour supermarket. Manager wants to know how to best handle the cash register during a midnight shift. Should he or perhaps she have one cashier all the times? Two cashier at all the times? Have one cashier at all times and a second cashier available? But only working as a cashier in the line gets too long, probably. So we have another free radical cashier that moves around it. This cashier might be doing other jobs. Probably, do you want one dedicated cashier? Do you want alternative cashiers because things might be on a different roles? They might like to have a break or something like that. Or you should have one cashier and a one floating cashier per se. Now, what kind of decision that comes around it? Each of this can be done during the operation hours. The managers can actually have these three circumstances, practice it for a week before he or she comes to a result. So an extra employee can be used to keep a track of the queue data and would not be too expensive. Differences are likely that not drastic, so the customers will not never be alienated. Don't use simulation if the system is too complex. To model correctly or accurately, this is often not very obvious, can depend on the cost alternative as well. However, a bad models may not be helpful and could be actually be harmful. With a space shuttle, lives were at risk. If the model predicts incorrectly, the result would have been catastrophic per se. We are talking about system, a group of objects that are joined together in some regular interactions or interdependence towards the accomplishment of some people. This was stated by Banks way back. Note that this is all very general definition. We will represent the system in a simulation using variables, objects, and operation thereby. The state of a system is the variable and their values at any one instances in time. Let me talk about discrete versus continuous system. Discrete systems state the variable change at a discrete point in time. We are talking about the number of students in any program. When a registration or add is completed, let's say number of students increases. When the drop is completed, the number of student decreases. Now these are discrete system that comes around it, which tells me the variable changes at certain point of time. So what is continuous system? States the variable change continuously as often as possible on a real time basis. For example, the volume of carbon dioxide in the atmosphere. Carbon dioxide been generated via people, breathing, industries, natural events, and is being consumed by plants thereby. So it's a continuous system that goes around us. Absolutely. Some definition models of the continuous system typically use differential equation to indicate the rate of changes per se. Now, what are we looking into it? Note, if we make the time increment and the unit of measurement absolutely small enough, we may be able to convert a continuous system into a discrete one. So we can have small batches and that would be discrete. However, this may not be feasible. Why? The reasons are plentiful. Also, note the systems are not necessarily exclusively discrete and exclusively continuous. They might not be the case every now and then. Remember, studying a discrete system, it makes some kind of adjustment, and we can predict some certain kind of outcomes or behavior. But continuous system, it needs to be continually updated, and things get changed as often as possible thereby. So we'll talk about system component, let's say entities, objects of interest within a system, typically active in one way or the another. Let's say we're talking about customers, employees, devices, machine, etc., that comes into it. For that can attribute certain information, certain attributes, either for the customers or for the employees or for the devices or for the machine. For example, for customers, it can be numbers of item purchase, usual number of total bills per se. How do we go around it? What about the activities within the system? For customer, it can be shopping, paying bill. In many cases, it's just really a period of time to perform the activity thereby. Note how nicely this meshes up with the object-oriented program in computer languages, which is known as OOPS, object-oriented programming as such. So events are instantaneous occurrence that may change the state of system. Note that the event itself does not take any time. How it goes around it. Note that they may change the state of the system. Example, when they would not, as on when on basis. So we can have an endogenous event that occurs within a system. For example, customer moves from one shopping to another to the checkout. right? So it's a part of the system. We can predict how much a customer is going to spend in the mall, in the shopping area, how much he or she is going to spend on the queue in front of the checkout, which is pertinent, and how do we come up with the query. And then we have, if we have an endogenous event, we should always have an exogenous event also, events relating, connecting to the system to the outside. Let's say customer enters or probably leaves the store, and that is what we are looking to it. So system model, a representation of the system to be used, studied in place of actual system, allows us to study the system without actually building it, which is, as discussed previously, could be expensive, which could be time consuming. So better avoid it. We're talking about a physical model. A physical representation of the system often can be scaled down. That is actually being constructed as often as possible to test that run on the model. Result used to make decisions about the system thereby. I'll give you an example of developing bouncing bombs in World War II, which we're doing around it. Remember, this is a physical model that comes around it. In fact, I would love if you can visit this site called sirburnswellis.com/bomb.html. I again can pronounce, I'm giving you a dictation, Sirs Barnswellis, SIRBANSWALLIS.com/bombs, and you will have the details of development of the bouncing balls in World War II per se. Most things done on Mythbusters is another example that comes around it. We will now talk about the mathematical model that comes around it, that can be represented as system using some sort of logical and probably mathematical relationship that comes around it. Let's say a simple equation about what happens for a temperature changes and variations as far as altitude is concerned. This equation can be used to predict distance traveled by an object in terms of time. However, will acceleration be the same cost? What will happen to it? Often this model is fairly complex, defined by entities and event. This is the model we will be using probably. However, in order to be useful, the model needs to be evaluated in certain way. The behavior based on the model needs to be determined, needs to be verified. So let us understand the analytical evaluation. If a model is too complex, we can sometimes solve it in a closed form using analytical method, absolutely closed form, isolating any other factors that can impact the model thereby. Now, why are we doing this? Because this is another type of analytical evaluation in the Markov process, or some people might say as Markov chain. Now, we're talking of this thing. Again, please visit Wikipedia. Visit Wikipedia and look for the examples of Markov chain, and you will see a plentiful of example, and host of example in Wikipedia. The audiences would love, and it will be a eye openers for every one of us out there. Every time I go there into the Markov chain, it actually fascinates me. Often the problems that are too complex, even they can be modeled analytically, can be computed intensive to the practical orientation, simulation, evaluation. More often than not, what we need to simulate is the behavior of the model by far. Now let us go to the deterministic model. Inputs to the simulations are known as no random variables. Absolutely no random variables are used. Example, customer arrives to a store are monitored over a period of days, and the arrival times are used as an input for the simulation thereby. And that is what we are looking forward to. What happened with stochastic model? Stochastic models are where one or more number of random variables are introduced in the simulation. That is what stochastics model is all about it. Results can be given only interpreted as an estimate or an educated guess of the true behavior of the system. Allow me to look into the quality of the simulation. Depends heavily on the correctness of the randomness of the data distribution, which might be more than the different situation that can require those distributions there per se. I'll give you an example. For example, the customer arrives at the store with exponentially distributed inter-arrival times, having a mean of 5 minutes, right? In most of the cases, we do not know all the input data in advance, or at least some random data is required. Thus, the simulation will typically use a stochastic model per se, as the cases might be. We look into the static model. The models a system of a single point rather than over a period of time. And that is what fixed, almost a fixed model that we are looking into it, sometimes also called the Monte Carlo simulation. Well, we will have a discussion, and this is quite an interesting discussion for Monte Carlo simulation thereby. But before that, we need to understand the dynamic model. Models over a system over a period of time, absolutely, which keeps on changing as the passage of time. Remember that thing, the simulation needs to be typical used to model. In summary, we will talk about discrete, mathematical, stochastic, and dynamic model for you to understand. With this, I come to an end of this presentation. Thank you for watching this video till the end, and we will have understood exactly about everything about simulation. Thank you once again.